Welcome back. This is Tutor Wizard. I'm Adrian. This is Alice. This is Ringo. Please subscribe right over here. We're doing a history of mathematics. This is ancient Greek math. This lecture, what we're going to do is Diophantine equations. Specifically, what we're going to do is linear non-homogeneous Diophantine equations in two variables, and we'll give the general solution in every case. Let's get to it. All right, first of all, for some terminology, for linear Diophantine equations in x and y, what do we mean? We're looking for, first of all, Diophantine means x and y are in z. We're looking for integer solutions. That's what the Diophantine means. If we're just looking for the equation, then we can find any real numbers. This isn't so bad, but we're looking for integer solutions specifically. Therefore, we have the general form of a Diophantine equation, which is linear in two unknowns, is going to be ax plus by equals c, where a, b, c are going to be fixed numbers, 2 and 3 and 5 we're going to do, or something like this. We're going to fix those numbers, and then we're going to be looking for x and y are the unknowns to be found in pairs. What do we mean by a solution then? A solution is any pair x and y which makes this equation true. And then what we mean by solve is we want to find all of the solutions. Moreover, if we let c equal 0, then that means that we get an equation that looks like ax plus by equals 0, and this is going to be called a homogeneous Diophantine equation. The story is going to be we need to find a homogeneous solution and some kind of particular solution. We're going to use the Euclidean-Bezuitan algorithm to find the particular solution cleverly, and then we can get the general solution to non-homogeneous. Otherwise, it's called non-homogeneous. Otherwise, if c is not equal to 0, ax plus by equals c not equal to 0 is non-homogeneous. All right, let's do the homogeneous case first, and then we'll do the non-homogeneous case, and then we'll give you a general idea of how to solve all of these guys. All right, for the homogeneous Diophantine equations, first what we're going to do is I'll do this all in one. We'll do the general scenario of the a's and b's and the c's in this business, and then I'll do an example right beside so that you can see with the numbers what we're talking about. We'll give the general solution to this. So cleverly what we're going to use is we're going to use commutativity of the real numbers, which means a times b is b times a, and then we're going to multiply by k cleverly, and then we'll get all of the solutions. What we're going to do is we're going to solve and move one of these to the other side. And so what I'm going to do is I'm always going to move to the y to the right hand side. It doesn't really matter, but I'm going to write this as ax equals negative by. And then over here, I would have 2x equals negative 7y. So I move this guy over. What I want to do with that now is cleverly use commutativity. I know that 2 times negative 7 is equal to negative 7 times 2. So 2 times negative 7 is equal to negative 7 times 2. And then what I'm going to do is multiply by any integer k, and then I can get 2 times negative 7k, put the k on this side, and then negative 7, put the k in the brackets on this side. And then now look at that. Oh, what that says is, what was I looking for? I was looking for a 2x equals negative 7 times y. So what does that tell me? If I match this in brackets and match vertically, this tells me that this one is equal to this, and so this tells me that x is equal to negative 7k and y is equal to 2k. These are the infinitely many solutions. So if there is a solution, there's always going to be infinitely many. Also notice that for the homogeneous, there will always be a solution, because 2 times 0 plus 7 times 0 is 0 plus 0, which is always 0. So x equals 0 and y equals 0 is always a solution to the homogeneous. And that's when you would pick k equals 0. But in particular, we have infinitely many non-zero pairs as well. So what are we saying in the horrible general scenario? We're saying the exact same thing. This would be if and only if I multiply this one by negative b equals negative b times a, then what I'm going to do is multiply by k, any integer, and that's going to give me a negative bk equals negative b times ak. And then what does that tell me? The general solution is going to be x is going to equal negative bk and y is going to equal ak, where k is any integer. This is the infinitely many solutions for homogeneous ones. Now what we want to do is make this c not equal to 0 and find all of the solutions. The homogeneous solution will be part of the general solution for the non-homogeneous case. Let's look at a couple of those. I almost forgot, so when we're still doing the homogeneous case, also note that the first two numbers I picked were relatively prime, which means that their GCD was equal to 1, and then you won't have to reduce the equations. But if I look at this one, and I just look at, without reducing, I notice that the GCD of 4 and 6 is 2, but we're going to have to reduce this equation to find the general solution, otherwise we might miss a solution, and we don't want to miss any. We've got to get them all, because we're trying to find all of the solutions. I know, it's exciting. Kitties are yelling in the background. So what do I mean by this? If I just do the same thing as we did last time, equals 0, and just multiply, so I'm going to move the 6y to the other side, negative 6y, and then of course I can multiply by negative 6k on this side, and negative 6 will be 4k on this side. That's our trick. Multiply by the opposite number as the guess, and then multiply by k. That will tell me that x is going to be negative 6k and y is going to be 4k. Why is that okay? Well, I can find a solution that's not in there if I pick the solution. If I don't reduce, what's going to be the difference? If I do reduce by the GCD, that's going to give me 2x plus 3y equals 0. So what we're going to do is we'll miss a solution. So now if I do the same thing with this reduction, and then let's see what would have happened. So if I pick, this will be 2x equals negative 3y. So we're going to reduce by 2, which is the GCD of 4 and 6. If I do that this time, then I'm going to get 2 negative 3k is equal to negative 3 times 2k. So that says that the general solution is going to be negative 3k and y will be 2k. So if I pick k equals 1 in this case, I see that 2 and negative 3 are a solution. So if I picked 4 times negative 3 plus 6 times 2 is negative 12 plus 12, which is 0. So this is a solution. So this value x equals negative 3 and y equals 2 is a solution to this Diophantine equation, but it will never, I can never get it by doing multiples of negative 6 and multiples of 4. So we've missed the solution if I don't reduce. So the first rule is, whether it's homogeneous or non-homogeneous, step 1 will always be find the greatest common divisor, and if it's larger than 1, reduce the equations by the GCD so that we do have relatively primeness. So that's the first trick. Always reduce. So the general solution is this guy, not this one. I know, kitty, that's crazy. All right, for the non-homogeneous case, what we're going to do is first theorem, let a, b, c be any integers, and consider the non-homogeneous Diophantine equation ax plus by equals c, and let d be the greatest common divisor of a and b. Then we have two cases. If the greatest common divisor of a and b doesn't divide c, there's no solutions. If it does divide c, then there's infinitely many solutions in the form, this form, where we have an x homogeneous and an x particular, and a y homogeneous and a y particular. What are those specifically? They are the associated x homogeneous and y homogeneous are, we ignore the c temporarily and look at equals 0, and then we solve that, and that's the associated homogeneous equation, or solutions to the homogeneous equation. And then the y particular and x particular, or any, we have to beg, borrow, and steal. We're going to use the Euclidean-Bezusian algorithm to find any particular solution to the non-homogeneous equation. This is essentially mathematical form for, if you look at the proof, the Gore details, it'll show you how to construct this. That's what I'm going to do in the examples specifically. So let's look at an example of how to actually do this in detail. What do you have to do? You have to do two battles. You have to find the homogeneous solution and any particular solution to these non-homogeneous Diophantine equations, and then you will have the general solution. Let's get at that. All right, for the first example, what we'll do is we'll compute where we don't have to reduce by the GCD, and then we'll do one where it's larger and we have to be careful with this. What do we have to do with this? Essentially, it says that the general solution, what we need is a homogeneous solution. Which is going to be x homogeneous and y homogeneous. And then what we need is a particular solution to, what do we mean a homogeneous solution to? We want in general, so this is going to be 2x minus 7y equals 0. And then we need any particular solution to equals this equation. So what are we really doing with this? Basically, so the first thing is we need to find a homogeneous solution to the associated homogeneous equation, and then we need a particular solution to the non-homogeneous equation, any particular solution. How do we do that? Essentially, we're going to do that in two pieces. For this one, I might just ad hoc guess, but you're like, I want a systematic method for that. That will be the Euclidean-Bozusian algorithm. But for now, we'll just show that this is how we build the general solution. How do we get this one? Always, I do 2x equals 7y. I bring this one to the other side. It was already negative, so it becomes positive. I multiply by the opposite number, and then by k. And then I'm lining this up. What I'm looking for was x is going to equal this, and y was going to equal this, because I've matched the 2's and the 7's. So this says the homogeneous solution will be x homogeneous is going to equal 7k, and y homogeneous is going to equal 2k. Therefore, I have the homogeneous solutions. That's the general solution to the homogeneous equations. Now I need a particular solution. You can do this any way you want, beg, borrow, and steal. If you can find two numbers which makes this work, then we're good. If I do 2 times 8, for instance, is 16, minus 7 times 2 is 16 minus 14, which is 2. So what does that say? A particular solution is x equals 8 and y equals 2. That is a particular solution. I found that ad hoc. This was in just brute force guessing, essentially. I will give you a systematic method in a second, but this is the particular solution, and this is a homogeneous solution. This says the general solution is going to be x and y equal x homogeneous plus x particular, y homogeneous plus y particular, which I can write now as 8 plus 7k. I flip them around. You can put this in the other order if you want. So I can say x particular, particular, homogeneous, homogeneous. And then this is going to be 2 plus 2k. This is the general solution where k is any integer. And this gives me infinitely many solutions. So the GCD, first of all, I didn't check, but the GCD of 2 and 7 is equal to 1. And 1 divides 2. So there's infinitely many solutions to this equation. And then what do I need to solve this? Because in my head, and I forgot at the beginning, that should be step 1 always. I'll do the systematic steps now to do this. But step 1 should always be compute the GCD of 2 and 7. You can ignore the negative of 2 and 7. It happened to be 1. 1 divides 2. Therefore, there must be infinitely many solutions in the form of the particular solution plus the homogeneous solution, which in this case is 8 plus 7k, and y is 2 plus 2k. Let's do this one more time where we have to reduce, and let's give the general formula for finding a particular solution. All right, for example, 2, I've multiplied the last equation by 2 so that we're going to get a GCD. So first of all, step 1 in our algorithm should always be find the GCD of a and b. So we have the GCD of 14 and 4 is what we're going to find. We'll ignore the negative. I'll show you how to deal with that in a second. Then what I want to do is, this is going to give me 14 is equal to 3 times 4 plus 2, and 4 is 2 times 2 plus 0. So the GCD of 4 and 14 is equal to 2, and 2 divides 4, which is the C. In this case, happens to be the same thing, but okay. So infinitely many solutions. What do I do with that? I proceed to step 2. If it's the GCD doesn't divide, then we don't have to do anything. We can stop and we're done. You just say no solutions. Step 2, we're going to find homogeneous solution. Step 2 is going to be, first of all, we reduce the equation by the GCD. So we're going to get, we divide, so 2x minus 7y equals 2. And then step 2, what we actually want to do is we want to find the homogeneous solution and a particular solution. So what we'll do first is we'll find the homogeneous solution. How do I do that? I want to look at 2x minus 7y equals 0. That's going to give me 2x equals 7y, if and only if we already did this, but this will be 2 equals 7k, and then 7 equals 2k. So that was, I was looking for 2x homogeneous equals 7y homogeneous. So this gives me the homogeneous solution. X homogeneous is equal to 7k, and y homogeneous is equal to 2k. This is half of the battle. Now we need a particular solution. Either I use the quotients I already had, I'll do this in one more example, but I either use the quotients I had or I find the GCD of 7 and 2. 7 is 3 groups of 2 plus 1, and 2 is 2 groups of 1 plus 0. So now the GCD is 1, which I need. I have to write 1 as a linear combination. You can use the Euclidean table, but in this case I already see that's what I'm going to get. 1 is going to equal 1 group of 7 plus negative 3 groups of 2. Cat's excited about it too. He's howling in the background. So what do I do with that? Now what we were looking for was rearrange this guy. I want that thing to match this. So I want a 2 to equal something times 7, negative y times 7, plus something times 2, which is the x. So I'm just grouping the original equation that I'm trying to solve for a particular solution. The clever idea is if I can write the GCD 1 as a linear combination of 7 and 2 now, I can write 2 by multiply. So now if I take this equation and then multiply this one by 2, then I'm going to get, and I distribute that in there, I'll get 2 equals 2 times this guy will give me 2 times the 7, plus 2 times this guy will give me negative 6 times the 7. And I get a different particular solution. What that gives me is, and then I was looking for 2 equals negative y times 7 plus x times 2. And then I vertically line this up, and it gives me the particular solution. What does that say? It says x particular is equal to negative 6, and negative y is equal to 2, or y particular is equal to negative 2. This gave me a particular solution, which happens to be different than the one that I guessed at, but there's infinitely many solutions. It will appear somewhere. Therefore, what do I have? The general solution is step 4, which is essentially just writing it together. And step 5 could be check if you want, but step 4 is going to be the general solution is a combination of the particular solution and the homogeneous solution. So the general solution is x equals x particular plus x homogeneous, which in this case is negative 6 plus 7k, and y is equal to y particular plus y homogeneous, which is negative 2 plus 2k. This is the solution. This is the infinitely many solutions where k is any integer. How do I find them? I first, step 1, I find the GCD of A and B on the left-hand side. If that greatest common divisor divides C, the non-zero number on the right-hand side, we have infinitely many solutions. If I have infinitely many solutions, then they're in the form of homogeneous solution plus particular solution. I find the homogeneous solution by reducing the equation by the GCD and then finding the homogeneous solution to this. And then for the particular solution, I reduce the equation again, and then I do this clever trick where I use the Euclidean Bazouchian algorithm to write 1 as a linear combination. Then I multiply by the number that I needed, the 2 in this case, to write as a multiple of 7 and 2. Then I'm matching the coefficients and finding a clever particular solution. Once I have that, I have a systematic method of finding the homogeneous solution and the particular solution, and therefore the general solution to these Diophantine equations. Let's try that one more time with a little bit longer Euclidean Bazouchian algorithm. Cats are attacking me, so I gotta finish up. This will be our last one, and this should give you the entire encapsulation of how to do the Euclidean Bazouchian algorithm inside to find a particular solution, then find a homogeneous solution, then we can find the general solution to non-homogeneous linear Diophantine equations in 2 variables. What are we going to do? First of all, I have the A's and B's are 95 and 60, so I want to find the GCD of the left-hand side. So I look at 95 is 1 group of 60 plus 35. Now I played the same game. 60 is one group of 35 plus 25. 35 is one group of 25 plus 10. 25 is two groups of 10 plus 5, and 10 is two groups of 5 plus 0. So the GCD is 5. What do I do with that? It turns out when you reduce this equation, the quotients are going to be exactly the same. So the first thing I do is reduce this guy. I'm going to reduce the equations, but the quotients are going to be the same that I need for this. So this says that, this is step 1, the GCD of 95 and 60, is equal to 5, and 5 divides 385, therefore infinitely many solutions. Now what do I have to do? Reduce the equations by the GCD 5. So that says 95 is going to be 19 times 5. 60 will be 12 times 5. 5 feet is 60 inches. And 385 is going to equal, either you have to do it or you have to cheat. That's going to give me 77 times 5. Again, just use long division, divide 5 into 385, and it won't be that hard. You're going to get 7 to be 35, and 35 will be 77. So now I have this. So what does that say? I can reduce my equation and consider the equation, instead of not 95, instead of looking at that equation, reduce. So that says I'm going to cut the 5 out of everybody. That will give me 19x plus 17y equals 77. This is the equation we're going to have to deal with. Now let's keep that equation and move everything up. All right, so now that we have the reduced equation, what I want to do with that is, again, find a homogeneous solution. So I'm going to look at 19x plus 17y equals 0, if and only if 19x equals negative 17y, if and only if 19 equals negative 17k, and negative 17 times 19k. So that says x, this will tell me that x homogeneous is going to equal negative 17k, and y homogeneous is going to equal 19k. Therefore, I have the homogeneous solution. And then what do I need? I need a particular solution. How do I find that? I use the Euclidean-Bossuysian algorithm. I kept the quotients from the Euclidean algorithm that I already used because I don't have space on the board, but you already have that on your page or wherever you're writing this. So I use the quotients for this to find the combination of, to write 1 as a combination of 17 and 19 cleverly. Then I'm going to multiply by 77. So what I cleverly want to do is or we can just do this again to show you, but it will be the same quotients, you'll see magically. So 19 is one group of 17 plus 2. Or sorry, that should be a 12, not a 17. We reduce. Sorry, it was a 17 or a 19 and a 12. Did I get those right? Yeah. So we get a 19 and a 12. When I want to reduce this, 19, let's run the game again. 19 is one group of 12 plus 7. 12 is one group of 7 plus 5. 7 is one group of 5 plus 2. 5 is two groups of 2 plus 1. And 2 is two groups of 1 plus 0. So now the GCD is 1. But look back at the last calculation we did. Once I cross off the last row and then use these quotients, it's the exact same quotients I used from the larger numbers, because we've reduced each of these equations by 5. We just cut the 5 out of every equation. So the quotients are the same. You can use those from the first calculation or forget and do it again. Either way, what do I need with those now? I need a table. So the first 2, and then I need 4 more. So no, no, and then I get 2, 1, 1, 1, 0, 1, negative, plus, negative, plus, negative, plus. This will be on 19, this will be on 12. Now you'll see the clever idea. I'm trying to write 1 as a linear combination of 12 and 19. Then we'll multiply by 77 to get a clever particular solution. Once I do that, what do I get? This says, what do I get? 2 times 1 plus 0 is 2. 1 times 2 plus 1 is 3. 1 times 3 plus 2 is 5, and 1 times 5 plus 3 is 8. Fibonacci sequence we got essentially. Therefore, this means that 1 is equal to negative 5 times 19 plus 8 times 12. And so then we're going to multiply by 77. When we multiply by 77, I cheated, but 77 is going to equal 77 times negative 5. We cut that out, so that should be negative 385 times 19 plus 77 times 8, which again, I can cheat, and that's going to give me 616, or just multiply that out. Just multiplying 77 by 8. So you're going to get 56, and 56, so 61. So make these calculations. Now what does that say? Why is that good for us? Rewrite this equation down here now. And that says I was looking for 77 to equal x times 19 plus some number y times 12. Don't be shy. I'm trying to match these things, so make everything line up. What that says is the particular solution is this guy and this guy. So now I have a particular solution. X particular is equal to negative 385, and y particular is equal to 616, which I found using the Euclidean Bose algorithm by writing the GCD1 after dividing by the GCD as a linear combination of 19 and 12, and then multiplying by 77 and cleverly matching everything. Once I have that guy, what is the general solution? Let's move everything up. All right, if I move all of this up and keep the information that we had a homogeneous solution and a particular solution. This says that the general solution is equal to what? X is equal to x particular plus x homogeneous, which is negative 385 minus 12k in this case, and y is equal to y particular plus y homogeneous, which is equal to 606 plus 19k, where k is any integer. This is the general infinitely many solutions to the non-homogeneous linear second order or in two variables Diophantine equation. Please subscribe right here. I'll see you next time.